Thank you, thank you, thank you. Glad to be back. Been out a while. You know, I've been on the road quite a bit this month. Got a lot of stories to tell, but this time I think we're going to take a detour into fire protection challenges in chemical and power plants, right? You clicked on the video, so let's get into it. We're going to talk about what the challenges are. I'm not necessarily going to teach you what a wet pipe system is or a dry pipe or pre-action, any of that. There's plenty of information out there for you to get that. And if you're already an engineer and you're working in this industry, in the energy industry, you're probably familiar with those terms, at least. And we're going to talk more about what can go wrong, what we can find out there doing our testing, and just, you know, basically how to make sure that this equipment works. So we're going to talk about the problems in the equipment in power plants and chemical plants. We're not really going to get into what the systems are. They are in high-risk facilities, so it's important that they are reliable. And what we do to keep them reliable is inspection, testing, and maintenance, ITM. That drives the reliability of the fire protection program. Okay, so let's talk about some common things we discover with inspection, testing, and maintenance. System impairments have to be number one. That's kind of the number one reason for systems not to be working is that they're shut down. And we find that because of inspection, testing, and maintenance. So it impacts the readiness and response of our equipment. These systems can get complicated. You can think of Rube Goldberg, and for you young folks out there, go Google it to see who Rube was. But the trim on a fire protection valve can be confusing, and it can be very easy for someone to accidentally disable an alarm or disable a system, or actually cause several systems to accidentally operate just by closing one control valve or one water supply valve. So it's something to be aware of. Now, what else do we discover? We discover component failures. Things break, right? Well, that's why we're testing, is to see if they still work. So in pumps, valves, sprinklers, detection system, what happens? In pumps, we can wear out impellers. That's not so much breaking as much as wear and tear. It does affect the performance. In valves, we can have drop gates, and that's where your stem breaks off and your valve is closed, but it looks like a stem is up, so it looks like it's open. That's bad news. The other one is for sprinklers. Obstructed heads. We see sprinklers actually getting not just obstructed, but loaded with different products in the facility if it's chemical manufacturing. And then we could get false alarms from detection systems. Here's one of the cleanest, prettiest fire pump rooms I've seen in a long time. I haven't been in one like this in a while. So what are the issues with water supply we can discover through ITM? We can discover pressure, flow, and where this will come into play is it impacts firefighting capabilities a lot, but also the fire suppression systems. If you don't have enough water pressure, you're not going to put enough water out of the few heads that first open. So what happens is more heads start to open, and then since you didn't have enough water pressure in the first place, they just start flowing less and less water through all these heads, and it just snowballs to the point where the system is running, but there's no fire suppression occurring. Right? You can kind of see in this hose, and fortunately it's only one person holding this hose, because that's a big hose. It looks at least 2.5, and if that thing was fully pressurized and he was flowing all what it could flow, he wouldn't be holding it. There'd be 2 or 3 guys holding that hose. So you can see that it's folded, it's bent. That kind of gives you an idea that it's not fully pressurized. So another challenge is scheduling and execution, actually performing the testing, the inspection, testing, and maintenance without disrupting operations. So we'll talk about some strategies to do that, but you have to realize you go into an office and you're going to do something with the detection system. Well, they may still need to be working in that office. Had an example when we were testing a fire pump at a nuclear power plant, actually all 3 fire pumps. We had gone to the control room. We got permission from the shift supervisor that it was okay to do it. And the next thing we knew, he had made a phone call to the plant manager, who had basically ordered us all in, canceled the fire pump tests, and wanted to know what we were doing out there in the middle of his plant. So it's important that everybody gets the message. I mean, we were only supposed to get the shift supervisor's approval, and he approved it, and then he turned us in and said he didn't want it done. So just communicate and work with the folks, find out what's going to be the best way to not disrupt their operations. All right, another challenge is in testing and inspection, testing and maintenance is good record keeping and keeping the documentation. I tell you, keeping the documentation is great, but that's not always enough. Let's look at the pitfalls with a lot of documentation. Has to be cut and paste. Can't tell you how many times I've read reports that have an electric fire pump data in a diesel fire pump form. So you can just tell that they've been cutting and pasting and they didn't read what they were doing. So be real careful about the records, keep them and make sure that they're accurate. Oh yeah, here's some old records. Been keeping those for a while. All right, another thing. Now let's talk about specifics of what can happen in chemical plants. Corrosive environments possible. It's not in all chemical plants, but it is possible, right? So the corrosion-related failures that we could have are in the piping itself, especially underground. We can see corrosion from the outside of the pipe. We can see, pitting and corrosion on the inside of fire mains too. The water condition has an effect on that. We also can see problems in detection systems. The corrosion, anything that's in the air can cause corrosion in the detectors. So you might start having false alarm. So we've got problems with corrosion. Now here we go. We have a sprinkler operating. Can anybody look at the sprinkler and tell me what's wrong with it in the comments, please? Because I'm looking at it and trying to understand, how's the water coming out? It looks like it still has the glass bulb in it, right? It looks like it's probably photoshopped. If that blue glass bulb is really water flowing, I'm shocked because I've never seen water that dark blue, that small of a amount. Let me know what you think in the comments. All right, now some specific problems in power plants. High voltage areas, control rooms, electrical rooms, anywhere you've got transformers. These are going to be fire protection challenges, okay? First off, when you look, this is a series of transformers at a power plant, and one of them is on fire. You see some very effective firewalls containing that fire. You don't see any real water spray. What you notice is the wind is drifting everything to my left on that screen. Make sure it's on your left. But basically the transformer that the fireball is over, if you look closely, that transformer, the paint is cooking off of it. The radiant heat from that fire plume above the non-affected transformer is roasting it, and its paint is cooking off, and I promise you those bushings are going to be damaged on top of it. Good to have firewalls. Can't count on them for 100% protection, so water spray is helpful here. That would have protected that transformer. Control rooms, okay? Again, can anybody spot the problem? Well, this control room, they're always a challenge for protection. They're generally manned 24 hours, right? So you don't really have to detect the fire. The people in there will detect the fire. The problem is controlling it without destroying the ability to control the plant and then losing control of the plant. So a lot of times we see gaseous systems or we see no systems and we just see detection with maybe operator action and a fire extinguisher, that kind of thing. We have videos on the channel where we talk about control room fires. If you're interested in those, ask me about them in the comments and I'll point you in the right direction. If you look at this picture, the problem is the windows, right? This control room is basically a fire trap. If they don't have rolling fire doors or some sort of fire shutters over those windows, any kind of turbine oil fire is going to approach that control room, and the operators in there, if they don't have a back way out, which has happened in the past, and there's been fatalities from this scenario. Operators were trapped in a control room. They found the drywall dust under their fingernails where they tried to crawl out the back wall because there was no door. So this is a problem. They need to either have water spray on the outside of these windows or roll up doors to keep the fire from coming into that control room. Sometimes the operators are stuck in the control room during the emergency doing emergency actions and they can't just run out. So it has to be an area that's safe for them to stay in. Where's another area of problems in power plants? Fuel storage and handling. We got a lot of it, so it can burn. The good thing is that most power plants, the fuel is not really flammable. It's generally the fossil fuels are oil or natural gas, which is fine if it's in the pipe, or coal. Still, we still have a lot of coal, so that's not typically a fast burning fire. But the fuel risks associated in chemical plants can get more in the flammable range versus combustible that we see in power plants. All right. The challenge, though, is even in power or chemical, is if you're already using foams with PFAS in them. So we had to deal with cold foam a long time ago, keeping it from freezing. So we used glycol and whatnot, and the foams are painted with the target of PFAS. So everybody's having to deal with that. Let me throw out there that F500 is a great alternative if you do not need to preserve the hydrocarbon that you're trying to extinguish the fire on. If all you're trying to do is extinguish a hydrocarbon fire, F500 is fantastic. It basically encapsulates the hydrocarbon cell, makes it mix with water, and then it's non-combustible. That's the problem. If you're trying to protect a large gasoline tank with F500, it doesn't make much sense to put the fire out and ruin all the product, right? So use it where it works, where for spills, for where you don't want fire, where it's okay to put the fire out. A couple of tanks just to spice it up a little bit. All right, in power plants, all right, this was, I'm going to give you some stories from my experience of my decades long working in power and chemical industry. But we had a series of ground faults that were shutting our fire protection system down, our alarm system. The alarms were going off so frequently that the operators duct taped a pillow to the alarm bell in the control room so that every time a fire alarm came in, it would be muffled by that pillow. That's unacceptable. It was a nuclear power plant, totally unacceptable, but we couldn't find the cause for all of these false alarms. Eventually we did. It turned out to be that humidity was getting into the conduit and finding its way up into the control boxes and then causing crystals to grow. The humidity was bringing, like especially down in the lower levels of the plant, any kind of moisture from underground soaking through the concrete, and you have a control panel up against that concrete, we would just see crystals growing on the insides of the terminal strips. That was our ground faults. It was intermittent. Once we figured that out, it was very easy to correct. We replaced them all, sealed the conduits, and the false alarm stopped. All right. Let's talk about another one. This was a very interesting one. This one was a GSU transformer, same nuclear power plant. And the job was to basically isolate the deluge system on this generator step-up transformer so that some work could be done. The operators went out to the valve house, and the generator step-up transformer had its own deluge system in a manifold with 3 other deluge systems. Those were for the standby for the standby transformers for the station service, auxiliary. So if we have additional transformers on site to run the plant, the big one was the one that takes the power out of the plant. Well, when the deluge system here was serviced, when they went to do the work, which was to basically clean the bushings, they had to take the deluge system off of the transformer. They got it off the transformer, and then they cleaned the bushings, and they went to put the pipe back up on the transformer. Little did they know, because they didn't look, but all of the drawings had the angles of where to aim all these heads. Well, the contractors just pointed them where they thought they should go, didn't really pay much of attention. Fast forward to the day we have to perform this tag out, and the operator's trying to tag out one system. He ends up isolating a valve that provided the priming water supply to 4 deluge valves. So as you learn your systems, if you don't have priming water, you're going to trip. There's a check valve to hold that priming water in, but check valves don't hold water forever, right? It slowly dripped out, leaked out, caused that deluge system to trip. And when it did, one of the nozzles was aimed across the high voltage bushings. Now this is 850 megawatt power plant, and you just arced 2 phases together. It was catastrophic, to say the least. So fortunately, it did not damage the transformer, and it only took about a week to get the plant back up and running. But also, unfortunately, was they didn't look at the other end of that high tension line that was connected to the turbine building, because within a week of going into operations, that disconnected from the building and fell on the ground. Okay, we discovered that our ground grid was not tied between the switchyard and the station when that happened, because then we had an arc jump from one ground grid to the other, and it caught the woods on fire outside of the plant. Okay, all this from inspection, testing, and maintenance. Right, let's get back to it. All right, well, it's another one. All right, so firewalls around transformers. They're great, and I showed you a picture of firewalls working, but what you have to be careful of is that you don't overheat the transformers. Those radiators need cooling. They have fans on them, and they need airflow. They need a way for the air to get to them. Now, what we've seen in the past is we've seen holes cut in the firewalls and fire doors put in so that normally it's open, but if there is a fire, the fire door can close. We've seen, and never do this, we've seen operators take fire hoses and spray them on the radiators. I remember telling a plant manager early in my career, I said, the last thing you want to do is spray cold water on a hot transformer full of oil that has gases dissolved in that oil. He said, why? And I said, have you ever poured Coke over a piece of ice in your glass? What happens to all the carbon dioxide when that soda gets cold? Its ability to hold that solution disappears. The colder the soda is, the less it can hold the gas. Same with transformer oil. The colder that oil is, the less gas it can hold. And if you cool it down while it's got gas in it, it's going to form bubbles. And if you have gas bubbles in your transformer, look out, because now you don't have cooling, you don't have insulation. You're going to have a quick failure of that transformer. Never. And this is not even to talk about the potential life safety of the people spraying the water on a live transformer. Never do it. What else happened in my history of problems with plants? Runoffs, okay? You got to be really careful about transformer systems, any kind of oil system or fire protection system that's involved with controlling oil fires, because you're going to spread the oil and you have to be ready for where that oil goes. And that's just a challenge of trying to control flammable liquid fires. Control the pool fire, control the pool first. All right, what else is a big challenge? Cooling tower fire protections. I fought so many times early in my career for cooling tower sprinklers. Eventually, I realized that they're never in service when you need them. They're corroded. I've even had like 6-inch elbows blow off of a system during a test because it was corroded. It's just a harsh environment for fire protection systems to live. A contingency plan for cooling towers is going to be much more effective, and you're going to get back up and running faster with a contingency plan than you are with an inoperable sprinkler system. The other thing about cooling towers is, you know, some of them now are made of fiberglass and they call it fire retardant. Just be careful about accepting what some tests under some conditions say that a certain plastic is going to burn. We all know that plastics will burn differently if you have them straight up and down versus if you have them laying across, if the flame's on top versus the flame's on the bottom. So you have to really check the tests that you're relying on to determine if it's safe. Underground leaks and locating and managing underground leaks. This is a huge challenge in big plants, chemical and manufacturing and power. The biggest challenge is knowing that you have a leak. And typically you know that you have a leak if your jockey pump can't keep up with the pressure, right? If your electric keeps starting because the jockey pump's running continuously, or you find yourself installing larger jockey pumps, it's time to start looking for leaks, okay? I've talked about it before, but the quickest way to do it, ultrasonic. If you find it, do ground penetrating radar, look, see how big the void is. If the void's not around a joint in a pipe, you might be able to get away with it, waiting for a while. If it's around a joint in the pipe, you got to be really cautious, because that could lead to a catastrophic failure where you lose the underground and it excavates a large hole. Okay, so this isn't what it would look like. This is small compared to what would happen with an underground blowout, but just giving you an idea. Other challenges, transformers inside buildings, oil-filled transformers inside buildings. It happened a while ago in the last century, we'll call it, but they're out there. So the big problem with these is they're huge fires. Even if the oil is all still in that containment, that's a huge fire, and just throwing water at it's not going to put it out, because the core of the transformer is going to continue to fail and burn. Whatever started this fire is not going to end until the energy's disconnected. Battery rooms, huge challenge. One of the things that you have here is the hydrogen. A lot of people don't really think about it because when a battery room's on fire, it's just the plastic that's burning. It's the cases that are burning. It doesn't happen often. Explosions can happen. I've seen a picture from one, not been involved in any investigations from them. What is so interesting about this picture? If you've ever looked in a battery room, you've probably never seen such a creative use of these swimming tubes, these styrofoam protection. They've got them covering all the connectors so that you can't drop a wrench or accidentally touch. It's not high voltage, but it's something that would cause a very loud explosion if a wrench dropped on it. I'm going to talk to you about a problem that I had and how I designed a system not to work. And this image is just to give you an idea of what we were dealing with. And this was when I worked for a gas and electric utility. The deal was we had to remove all of our underground combustible liquid or flammable liquid storage tanks. We had to move them above ground and put them in buildings, or just get them above ground. They were not allowed to be underground anymore unless we put all kinds of crazy containment and monitoring and all that. So we had a facility that had a 1,000-gallon ethyl mercaptan tank underground. Ethyl mercaptans are used to odorize natural gas. The strength of this mercaptan is so high that if it were leaking, if you were to walk into a room with this, that first off, it doesn't have to leak. It can soak through 3/4 of an inch of steel. So your tank, 3/4 inch of steel, it will still soak through it. So that's why we had it underground, so you wouldn't smell it. You put it up in a building, now you're going to start to smell it. You have to have a ventilation system that can absorb all those smells. So we have a charcoal ventilation system. And the fire department looks at it and says, you've got a 1,000-gallon tank. It's flammable liquid. The building code says you have to have suppression in there. We went and we talked to the fire marshal, said, if we suppress that fire, people for miles and miles around will become ill, nauseous, headaches, vomiting. You're not going to be able to control the emergency that's caused by the smell of this. Everybody's going to be reporting gas leaks everywhere. So if there is a gas leak, you won't know it. And we just talked for a while. We tried to convince him. And finally he says, I'm not going to argue with you. It's the code. And he just said, do it. So we said, okay. I went back to the project team. I said, we can go over his head. He's just a fire marshal. Should we do that? They said, no, let's get along. Let's work with him. Just put in a system. I said, all right, but the last thing we want is for it to work. We're going to design a system that will not work. We'll put in a CO2 system. And just so nobody gets trapped in the building, we'll put in a 60-second time delay. And that's acceptable so that people can get out before the CO2 dumps. And just to make sure that this hot fire that we've got going in there doesn't destroy the building before we get a chance to dump the CO2, let's put in smoke and heat vents. Any good fire protection engineers know where we're going with this, right? So we've got smoke and heat vents, we've got a CO2 system, we've got a 60-second delay. What's going to happen when that fire starts? First thing that's going to open is the smoke and heat vents. The detection system is going to tell the gas system to start counting down and evacuate the people. When the people get out, the gas system is going to operate, and all of that gas is going to get pulled out of the smoke and heat vents by the plume of the fire. So fortunately, we'll have a system that will not extinguish the fire. And believe it or not, we actually designed a system on purpose to overcome that problem in this industry, and the fire marshals took it. So with that, let me just say thank you. It's been great doing this. If you have any questions or comments, please put them put them in the comments section. Send me some ideas if you want to hear about anything else in the energy space. I'm happy to do it. Thanks a lot. Talk to you all next time.